Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sababau from the Physics section, Pusat Pengajian Pendidikan Jarak Jauh University Sains Malaysia. This is course JIF 318 Quantum Mechanics. We are in chapter 5 on linear algebra, matrices and Dirac notation. This is unit 5.2 on vector spaces. The objectives of this segment or unit is for you to be able to explain how a set of functions can be treated as a vector space. Vector spaces are simply a collection of objects or vectors which act like the familiar 3D vectors. I think you are familiar with vectors in three-dimensional. A vector must have magnitude and direction. So if we have a collection of vectors, these can be treated as vector spaces. The sum of two vectors must also be a vector. For example, if you have vector r plus vector s, then you have another vector c, t here. Okay, so the sum of two vectors must be a vector. The product of a number c must also be a vector. For example, if you have a vector r multiplied by a number c, and c can be a complex number. When I said a number, it can be complex number. You multiply a number with a vector, then you get another vector u. For some vector spaces, c is assumed to be a complex number. Okay. In quantum mechanics, we will deal exclusively with complex vector spaces. Complex here means that containing complex numbers. The set of functions f(x) can also be treated as vector space. All this while, we have been talking about functions, okay, wave functions and so on and so forth. So, the function f(x) here can also be treated as a vector space. That means a function can represent vector spaces. Clearly, the sum of two functions f(x) and g(x) is also a function. Okay, if you have two functions f and g, then you add it up, then you get another function h. We can multiply a function by a real or complex number to get another function. That was said in the previous slide. If you have a function with a real or complex number, we have to get another function. Remember the two rules for the operators. For example, if you have f plus g, so it is equal to the function of a two variable is equal to two functions actually, and the second one is when you multiply with a number, then you get another function. In fact, the set of functions behave like an infinite dimensional vector space. Usually we are limited to three-dimensional vector space, but the set of function can be more than three. So the set of function behaves like an infinite dimensional vector space. In quantum mechanics, we agree that there are more than three vectors, three dimension. I mean, in theory, we can have infinite dimension of vector space. Okay, now let us consider, this is an example, a three-dimensional vector. I think this is quite normal. Okay, x, y, z. Okay, vector r equal to 149. But when we plot it, we can display this vector by plotting ri as a function of I. The x-axis is I. That means I is the number of vectors 1, 2, 3. Ri is the y-axis. The 3D vector can be represented by three dots like this. At I equal to 1, it is 1 here. Okay. Then when I equal to 2, the value of R is 4, it is here, then if the I is 3, the value is 9 here. Okay, so we can plot it in a 2-dimensional. We can plot 3-dimensional vector in a 2-dimensional graph like this. The graph is Ri against I. So theoretically, we can have more than 3D vector. For example, we have 7D, 7-dimensional vector. Again, we plot it Ri against I, then we can plot the vector spaces as dots here. Now it looks like it is following a trend there. Okay. And if we have n number of dimension, as we take the limit to n infinity here, the points become denser. That means the vector spaces here become denser and become connected, merging into a continuous curve. You have a curve here, and the curve is actually, when you want to explain the shape of the curve, it is a function. That means you have a formula for this curve. So it is a function. So you can say that vector spaces can be represented by a function. That's why it says that a set of functions represent vector spaces. This is what we call as vector spaces. So as a conclusion, a set of functions behaves like an infinite dimensional vector space depending on the dimension number. Okay, so if actually a set of functions, if we have a formula for a curve, then basically those curves can be considered as n-dimensional vector spaces. Thank you very much for your attention.